Right, so first of all, uh, for this course, let's develop a better way to write things down, right, for general relativity. So, so far, what we have done is we made use of matrices to represent vectors. And not only vectors, but in fact, we also, when we talked about the metric and the transformations, we used matrices, right? Well, it turns out that matrices sometimes actually really suck, right? And here, let me mention you the three specific reasons to why so. Well, first of all, the matrices, right? I'm talking about matrices, right? So these matrices can be very big, right? So you have to write them down like this, and you might have lots of elements in here, right? And well, if you have the functions of sine, cosine, and well, even variables, right? They can be extremely big, and writing them down explicitly can make you very tired, right? Well, I don't know about you, but it makes me hell of a tired, right? So that is one reason I would put over here that these matrices suck, right? Okay, so moving on to, we also know that matrices do not commute with each other. So that means when you're writing down expressions, we have to be careful about a particular order. So for example, if you have a matrix A and you have to multiply with some matrix B, you can, if you do A times B, or a matrix B times A, you would get different results, right? Because matrices do not commute. So let's say that means that the commutator of A and B is not equal to 0. And so we have to be careful about the order when we're writing these down. And finally, the most important one is that we will soon encounter objects and operations that cannot at all be represented by matrix multiplication or, well, matrices at all, right? And this is where the index notation comes to the rescue. And so what it happens is that the index notation will not only reproduce all of our matrix goodness, but in fact it would give you truly much more than you could have asked for. So, well, with all of this, let's actually look at a very simple example to get the basics, right? Or to get a basic idea, right? So for that, let's consider a coordinate system, or in fact two coordinate systems. So here you have x1, and here you have x2. And this is obviously a two-dimensional coordinate system. Here, say you have a point in this coordinate system, and that can be defined with these coordinates x1 and x2, right? So let's do something to this coordinate system. Let's rotate it by some angle theta. So, well, I'll just draw this original coordinate system right here first. So this is your this coordinate system, and let's rotate it now by some angle theta. So let's rotate it with some angle theta, and this, you get something like this, right? You get the point, right? Over here again, this is our x1 and this is your x2. But now this is your x1 prime, so x1 has been transformed to x1 prime by some angle theta, and here you have your x2 prime. And now you had this point in your coordinate system that was represented with x1 or it was defined with x1 and x2. Now it is defined by some other variables, right? x1 prime and x2 prime. So what we would like to understand over here is the relation between x1 and x2 to x1 prime and x2 prime. And we already know that, right, from previous videos. We can write that down as we have x1 and x2, right, and this transforms as x1 prime and x2 prime, which is simply equal to, because we have rotated our coordinate system over here, right? And so we have this two-dimensional 2 cross 2 rotation matrix, which is cosine theta, sine theta, minus sine theta, and cosine theta. And this matrix acts on your original coordinate system vectors, which are just x1 and x2. So this is in terms of matrix. Now what I can do over here is, let's just take this thing, right, and let's call it something else. So let's take this and let's call it that this thing is your lambda 1 1 prime, and here you have lambda 1 2 prime, and here you have lambda 2 1 prime and lambda 2 2 prime. Well, you might think that we have done absolutely nothing. We have just changed the name of these sines and cosines to some lambdas. But from this, what I can do now is I can write down all of this thing that I had over here as simply some x I transforms as xi prime, which is simply equal to lambda I j prime, right, times x j, right? And we know how to evaluate this, right? That is simply using the Einstein's summation convention, which is just that you sum over the repeated indices. So we have j is our repeated index, and you will sum over j. So j runs from 0, 1, 2, 3 generally, but of course for this example it just runs from 1 and 2, right? Okay, so well, we can write this down now, this thing explicitly, and we will see that we end up with what we had over here, right? So let's go ahead and do that. Let's write it down explicitly. So you have xi transforms as xi prime, which is equal to lambda I 1 x1, right? And we have prime over here, plus we are just summing this thing, right, over this j, so that is, which is our repeated index. And then you have lambda I 2 prime x2. These indices have to be immediately adjacent to each other, right? That's one way of knowing how to do this, right? Okay, so if you look at this thing, right, this thing gives you two equations, right? If you note over here, we had lambda 1 1 prime as our cosine theta, and lambda 1 2 prime as our sine theta, and likewise, right, all of these correspond to, so this one is corresponds to this one corresponds to this one to this, and this one to this. And so I can now open this thing out and write it as, for example, when I have I1, right, these I prime is 1, or when it is 2. So that means you get two equations, right, a set of two equations. Which are those? Well, they are x1 prime is equal to lambda 1 1 prime x1 plus lambda 2 lambda 1 2 prime x2, right? And if you look over here, what is your lambda 1 1 prime? Well, it is cosine theta, and lambda 1 2 prime is sine theta. So this simply gives you cosine theta x1 plus sine theta x2. And likewise we do it for x2. It would be lambda 2 1 prime x1 plus lambda 2 2 prime x2, which is simply minus sine theta x1 plus cosine theta x2. And well, bam, here you go, right? We used this index notation, and we could recover our original equations, right? This thing. And we had simplified. In fact, for me, it was a big deal simplifying, writing down all this messy stuff over here, right? So instead of writing all that down, we can simply write this thing. And that's very nice and neat. So from here, now let's quickly look at some of the important things before we jump into the wonderful pool of vectors. So in fact, we are done with talking about this part of the video, that was index notation. So we're not really done. Well, we're after I mention some of the important things, right, important properties, you may think of them, then we will immediately start with the topic of vectors. So well, let's just start, right? So number one is say for example you have pick any number, right? Say 38 number of dimensions. This expression would still be the same, right? So doesn't matter how many dimensions you have, this thing is not going to change. And what that means is that size doesn't really matter. Okay, so number two, we could have also written down something like xi transforms as xi prime, which is equal to xj r I j prime, right, which would be equal to x1 r I prime 1 plus x2 r I prime 2. And this would give you x1 prime being equal to x1 cosine theta plus x2 sine theta, and x2 as x2 prime as x minus x1 sine theta plus x2 cosine theta. Now you might be wondering, what the hell am I doing, right, by writing this thing like this? Well, in matrices, this thing mattered, the order mattered, but when using this index notation, we can definitely write this thing as this. So you don't think of this R I prime j as a matrix, right? You do not think of it like this. It is an object which has elements, where if you have defined I and j, you can write those elements down. And so one of the very important feature of this index notation is then that you can do this thing, right? You can do this thing. You can write down this object in front of your xj or any x, right? And so order does not matter. we will get the same thing if I use this thing, right? Or if I use R I prime j x j, right? So it doesn't matter. These two things are absolutely the same. But again, this is not true for the case of matrices, right? Okay, so now you can also immediately evaluate something that is of this form, say m ijk times n ijk, right? Of course, given the elements of these two objects, right? Uh, Even though you really cannot represent these objects in terms of matrix multiplication or matrices at all. So remember in the beginning when I said that one of the reasons why matrices suck is that we encounter objects, right, that cannot be represented as matrices. And well, here is the example of those objects, right? So okay, well, you may also have noticed that any time an index is repeated, right, it comes in an upper and lower pair, right? If you look at this thing, right, so if this in j is repeated and it comes in a pair of that it's lower index over here and it's upper index over here, right? Well, I'm not really going to talk about this right now, but you will eventually understand what this means and why is it like this, right? Okay, now moving on, in 4 dimensions, so when we talk about 4 dimensions, we will use Greek indices, right? So we would use mu, nu, lambda, and well, etc., right? And these mu, nu, and lambda, they take values that are 0, 1, 2, 3, right, in 4 dimensions space time. So what that means is then this 0 would correspond to ct, 1 corresponds to x, 2 corresponds to y, and 3 corresponds to z, right? Now in some cases you will see objects that have one prime and one unprimed index. And what that is it is just the transformation from one coordinate system to another. For example, consider this thing, right? X mu prime, which is simply a transformation of x mu with this transformation object, right? That is lambda nu and mu prime on x nu, right? Again, you see that they come in an immediate adjacent pairs. Well, in fact, this lambda mu prime nu will be the only object that we are going to encounter in this form, right? With this one primed and one unprimed. Any other object will either have all prime or all unprimed index. For example, you could take this object, for example, it's mu nu lambda, right? So they're all unprimed, or you could have some object that has all primed index, right? Something like this, right? Now, in some cases, you will want to revert back to matrix expressions, right? And of course, that is when you can, right? Because we said that some objects, they cannot be represented with matrices at all, right? Okay, so well, if you have to revert back, to do so, we have to identify the row and column of any two index object, as left would be the row and right would be the column. The up and down really does not matter at all. But to get the order right, because in matrices you have to care about the order, you just make sure that the repeated indices are immediately adjacent. So what that means is that for matrices, right, this thing, lambda mu prime nu x nu is true, right? So this thing works for us. However, and again this is for matrices, something like this, that is x nu lambda mu prime nu, this thing does not work. So it does not work. Again, this is the case when you have to revert back to matrices. And this thing, of course, this implies that you get something like lambda x, and this thing gives you x lambda. So right, in matrices then, this thing and this thing are not the same. Okay, well, we talked a lot about this index notation. With all of this now, we are absolutely ready to move on to the topic of vectors, right? And so, well, let's start. So we'll talk about vectors now. And well, space-time vectors, and that is what we are going to refer to as just vectors, right? So these space-time vectors, they correspond to real physical quantities with magnitude that may or may not be related to the space-time itself. For example, consider some quantity delta x, which is directly related to space-time, and E, that is the energy, it is not related to space-time. And we also have the directions, and the directions, they do correspond to the directions in space-time. So let's look at three of the most important features of the vectors. The first one is that the vector itself is invariant under a coordinate change. Now, more often it is very easy to understand, but sometimes it cannot be so easy to picture. So we'll consider that you have a momentum vector on an infinite cylinder. So consider that this is your infinite cylinder, and you have a momentum vector on this infinite cylinder. So if you would have a coordinate system that is, say, this is your x and y, and if I rotate this coordinate system, so let's say something like this, here this is my x prime and this is my y prime, the vector, this one, will have different components in each coordinate system, but the actual direction of this vector, it will not change, right? I mean, well, if it did, that would simply mean that it could go from an infinite direction to a periodic direction, and that is totally absurd. So well, moving on to number two, I said three important features, right? So number two is that the components of the vector should have well-defined transformations under any change of coordinates that are used to describe our space-time. And in fact, our goal in this lecture is to find or discover this law. Okay, so moving on to number three, well, despite your early experience with vectors, which may have been in terms of a ray that connects 2 points, point A to point B, right? Something like this. Or you could say an array that is connecting two positions, which could be, for example, a position vector with respect to origin. But the vectors do not in general live within a space or a space-time. And this is because the usual rules of vector manipulation that comes from linear algebra require these objects to exist in flat spaces, right? Which could be Rn or Mn, right? But note that the space or space-time, it can be curved, right? And of course, when we are talking about general relativity, we have to consider this fact that space-time is curved. And well, let's look at an example very quickly. Consider S2, which is, that's in topological language. S2 is just a unit sphere, right? And something like this, right? It's a sphere, and on this sphere, you say you have a point over here, and this point would have vectors, something like, say you have this tangent plane on this point, and so this would have then vectors like this and like this, something like that, right? Now, the question arises that how do we work with this intrinsically flat objects in curved spaces, right? Well, at each point in space, we will define what we call a tangent space. If you look at this diagram that I drew over here, you can understand that. And this tangent space as the set of tangent vectors to all the curves that are passing through that particular point. And the vectors at each point in the space, they live in these tangent spaces, right? Okay, so this statement or this fact, it has two important consequences. The first one being that we cannot freely move vectors in space, right? Since in general the tangent spaces will change. And number two is that comparing the vectors that are defined at two different points in space is going to be tricky for us. But well, to understand how to deal with these two consequences will require a lot of technology that GR or general relativity rests on, right? And that's what we are going to that's what we are spending our time before we move on to the Einstein's field equations and so on, to understand all of these this technology, right? So for now, let's actually start with a flat space. And in this case, what happens is that in flat space, all the tangent spaces are equal, right? So you could think this on this sphere, this thing that I draw, this is our tangent space, right? And on that we have these vectors. So to uncover how vector components transform under coordinate changes, we will first focus on a particularly simple vector, and that is ds, right? The line element. Now, the components of this vector are just coordinate differentials, right? Which are dx mu, right? So if we know how the coordinates themselves change, then we obviously know how the components of this vector change. So say you have x mu, and that transforms as x mu prime, which is equal to lambda mu prime nu x nu, right? And this thing then directly implies that the differentials would also transform, as dx mu transforms as dx mu prime, which is equal to lambda mu prime nu dx nu, right? Okay, so far we know how the components of one particular vector transform. But what we would like to know is to have a rule for transformation of components of any vector, right? Now, to find this, we are going to use a trick. And that is what we will also use when we extend our discussion of these vectors to general tensors, right? Because vectors are also form of tensors, and we'll talk about this in the next video. I'll talk about dual vectors, and after that we will talk about tensors specifically. So my point over here was that we are going to use this trick, and we will also use this when we talk about tensors, so pay attention, right, please. Okay, so recall that a vector is invariant under coordinate transformation. Now it's true that the components will change, components of the vector, but the whole thing better not change, right? So, how do we work with something like this? Well, recall that a vector is expressed as an expression in some particular basis. So say you have ds, this is your vector, and you can write this down as dx mu e hat mu, right? Now over here, this dx mu are your components, and this e hat mu are the label vectors. They're not the components, right? Okay, so yeah, let me draw this thing over here, that this over here is, this one is your x1 and this is your x2, right? Now, and the this labels, they tell you that the direction that we're talking about. So this is in fact we'll have e2 over here, and this direction is e hat 1, right? Now the trick that I said that we will use is that we want ds to be invariant, but then knowing how dx mu transforms, we can get how this e hat mu transforms. And let me show you how, right? So consider now this thing, all of this, right? This transforms as ds prime, which is equal to dx mu prime times e hat mu prime, which is equal to ds. That's what we want, right? It has to be invariant. ds has to be invariant under a coordinate transformation. So from this we can write then that this thing, dx mu prime, we can write this as lambda mu prime mu x mu. In fact, we would have dx mu, right? Because we are transforming this differential. Right. Now, and of course we would have this e hat mu prime, right? Which is in fact equal to lambda mu prime mu dx mu. And let's say that this thing over here, this basis, let's say, or let's consider this, that it transforms under this thing, that you have this lambda alpha mu prime e hat alpha, right? Let's just consider this and put this in our expression now. So what I would have over here is lambda alpha mu prime e hat alpha, right, in place of this thing. Now this thing, all of this is actually equal to dx mu e hat mu, or it has to be equal to this, right, for it to be equal to ds, which we want because ds has to be invariant. Now if we have or in fact, let me just do this one more step over here. This thing, we can write this down as lambda alpha mu prime. So we're just moving things here and there. Lambda mu prime mu dx mu e hat, what just happened? Yeah, e hat alpha, right? And this is equal to this thing, right? So that's dx mu e hat alpha, right? Let me just, yeah, it's e hat mu, right, from this thing, because it has to be equal to ds for it to be invariant. Now consider this, that if we have this lambda alpha mu prime times lambda mu prime nu, this is equal to this delta function, that is delta alpha nu. So of course when alpha and nu are same, this gives you 1. When they're not, it will vanish. This thing is simply lambda inverse lambda is equal to identity, right? So you have to remember over here this thing, that we had lambda transpose eta lambda as eta. This was our condition that we talked about in the video on matrix, right? So well, one of the thing that this thing tells you is that lambda transpose is not equal to the inverse of lambda, right? But okay, so over here yeah, in this one we were talking about, we needed a trick, right, to see how these bases and this dx mu transforms, right? And we use this, and you can see that indeed with all of this, ds remained invariant, because this final expression that we had over here, this thing, it is the same as what we started with over here, that is this thing. So with this then, ds is actually invariant. Now there is a lot of index going on over here, so don't get lost in all of this index gymnastics, I should say. The end result over here should be actually straightforward to you, and that is that if ds is invariant, then the components and basis vectors should transform in ways that cancel each other out. So well, what I'm saying is, if you look at this thing, Actually, just instead of writing it all down again, just look at this thing, right? And you can understand that the basis vectors should transform in ways that cancel each other. Now, now we have transformation law for basis vectors. We can recall that an arbitrary vector can be expanded, right, as say you have some arbitrary vector v, you can write that down as v mu and the base is e hat mu, right? And this thing, it should be invariant under a coordinate change. So before we go any further, let's just stop and think about this for a second. This actually tells you immediately, in fact, that the components of any arbitrary vectors must transform like the components that were dx mu, right? So now let me write down the transformation law for vector components and basis vectors, which would be the same. So we have v is equal to v mu e hat mu, right? This thing transforms as where this is your component and these are your basis vectors. This transforms as v prime mu e hat mu prime, right, which is equal to v prime, which is equal to v. The vector itself should be invariant. Now if we have v mu prime is equal to some object that is this transformation object mu prime and nu on v nu, then we have this e hat mu prime is equal to lambda alpha mu prime e hat alpha, right? That's how the bases transform. And we have this lambda alpha mu prime contracted with lambda mu prime nu is equal to this delta function alpha nu. So here we have what is the transformation law for vector components as well as the basis vectors. So I have actually just written all of this down over there again, well, neatly, right? So again, this is the transformation law for vector components and basis vectors. Now let's see how does all of this play out in a familiar example, right? Shall we? I mean, you don't have a choice, of course. So let's consider a vector v and its description in these two coordinate systems, right? So one we have x, y, and the other one is rotated in this way, right? Where you have y prime over here and x prime over here. So first let's consider this first one, which is this one, right? X and y. And in this you have this direction or this basis vector as j hat and this one as I hat, right? So in this, then you can write down your vector v as v I hat plus 0 j hat. Of course, I did not draw this vector v over here. The vector v is in this direction. So this is your vector v, right? And with this, then you have it can be written as this, which is simply equal to, in index notation, vi e hat I, right? And over here, this ei is, or actually just say this e is 1, e1 is I hat, which is in this matrix form 1 0, and e2, because we have 2 dimensions, right? So we would have only 1, and I would only go for 1 and 2. This is equal to j hat, which is 0 1 in matrix. Now this thing just says that v1 is equal to v and v2 is equal to 0. Now for this one, where you had rotated your coordinate system in a way that this is your x prime and this is your y prime, we have rotated the coordinate system with this rotation by 90 degrees. Now rotation by 90 degrees in 2 dimensions is a 2 cross 2 matrix, which is cos 90, sin 90, minus sin 90, and cos 90. If you evaluate this thing, you simply get sin 90 is 0, cos 90, cos 90 is 0, sin 90 is 1, and minus 1 and 0, right? Okay, now this thing, you can call this thing your r I prime j, right? Which is this matrix that is 0 1 minus 1 0. This is the matrix representation of this object. But to describe your vector v in new coordinates, we will first rotate the components by this 90 degree, right? So r90. So let's see, let's look at that. We would have a vi transforms as vi prime, which is equal to r I prime j vj, right? And this implies that your v1 transforms as v1 prime, which is equal to r. Now we are just summing over the repeated indices, so r11 v1, you'd have a prime over here, plus r 1 prime 2 v2. This thing is 0. Now v2 is or it transforms as v2 prime, which is equal to r 2 prime 1 v1 plus r 2 prime 2 v2, and this thing is negative v, right? But and here we have simply labeled these this 0 corresponds to r 1 prime 1, and likewise, right, like we did in the beginning when we were talking about index notation. So well, but then the basis vectors must be transformed by the inverse of this, right? So this thing, and it simply means that rotate by negative 90 degrees. So rotate in the opposite direction by 90 degrees, and the matrix for that it would be 0 minus 1 1 0, right? And you will call this matrix or this object as r I prime j, right? Now with this, then you can see that e1 hat transforms as E1 prime hat, which is equal to Rj I prime on E1, or let's write J over here first, and now let's sum over this repeated indices, where you would have R I prime 1 E1 hat plus R 2 I prime over here E2 hat, right? And this thing, or this expression, actually I wrote E1, I meant EI, right? This is EI. Now from this, let's write down the expressions for E1 and E2. I hope you forgive me for this confusion, right? This was EI. So I was writing down the general expression for the transformation of the basis vectors. Now I will, from this general expression, I can write down for E1 and E2. So let's write that down. E1 hat transforms as E1 prime hat, right? And well, we can write this down as R1 1 prime E hat 1, right, plus R 2 1 prime E hat 2, right? Now this thing is simply this thing, look at this, right? R1 1 prime is this one, and that's 0. So 0 times, well, you can write this down, E1 hat plus R2 1 prime is positive 1, and that is, then this will give you E hat 2. Now if you look at this, this vanishes, right? E hat 2 we define in columns as 0 and 1. Now let's look at E hat 2, which transforms as E hat 2 prime, which would be equal to, we'd do the same procedure, so we would have R1 2 prime this time, and E hat 1 plus R2 2 prime E hat 2, which this time would give you negative 1 for this one. So you would have negative E hat 1 plus it would give you a 0 for this, so you just have 0 over here. Now E hat 1 is 1 0 in columns, but with this negative sign we would have -1 and 0. Now you compare and see that this tells you that I hat prime is actually transformed into J hat, and your J hat prime transformed into negative I hat, right? You can see that from this. Now finally with this we have your vector V is equal to V I hat plus V J hat, right? Which is nothing but equal to, this is not in the subscript, by the way, this is like this, right? And with this transformation, now it turns out that the components and the basis vectors have transformed in this way, right? So you'd have 0 iota hat prime minus V J hat, right? And if you look at this and you go over here and you look at this coordinate system, which was the transformed one, this equation exactly tells you that exactly tells you that you would get something like this, which is what we had already expected because we started off with this transformation, right? by the rotation with 90 degrees. Right. So with this, we have talked enough about vectors as well. In this video, I talked about index notation, and the main thing was to talk about this transformation law for vectors, which we have properly discussed in this one. In the next video, we are going to talk about what is called the dual vectors. And believe it or not, you have already worked with dual vectors, right? In fact, since you were taking dot products in your elementary vectors, you cannot take a dot product without a dual vector, right? So we'll talk more in detail about that in the next video. And after that, we will talk about tensors.